Hello, in this video we are going to pick up with lesson 3 from part 2 inside of unit 4 for college algebra class. Much of the first half of this video is going to be done on your own, and I'll show you how these questions will play into our work with transformation of functions in just a moment. But essentially what I've done here is I've provided a table of data, or a table for data. I've provided x values and then the function associated with these values. So what I'd like for you to do is complete these tables based on the equation that's provided in each one, and then plot these key data points. For example, in this first table, when x is -3, well, y is equal to -3, and that produces the coordinate -3, -3. When x is -2, y is -2, and we've got the coordinate -2, and so on. And it would be appropriate, once your table is complete, to connect these data points with a line. So I'm going to go ahead and do so. You can use a straight edge and a pencil. If you want to sketch this freehand, that would be okay too. The drawing's not critical. For the second example, we can do the same thing. -3 squared is +9, -2 squared is 4, and so on. So with the table complete, we can plot these data points. Now those points have been plotted, and this isn't a straight line, so we'll try to connect these points with a smooth and continuous line. Generally, when I sketch these, I use these little short pen strokes, but my goal is to try to make this appear like it's a smooth and continuous line. It's a parabola that we're familiar with. So what I'd like for you to do now is just pause the video and complete the rest of the sketches here. There are times where the input values will not produce a real number result. For example, down here, if I try taking the square root of -3, and you can simply write DNE for does not exist. So if you encounter that elsewhere, go ahead and mark that as DNE and plot the points that you can. Resume playback in a moment to check your work. Okay, and you should have some results here. In this particular example, there were no surprises. Just keep in mind that when a negative number is raised to the third power, it does remain negative. In this example down here, this middle row, I found that the data points that we provided may not have provided a complete view, so I went ahead and added a couple, and I just noticed a small mistake here that I've just corrected. So when the x value was -3, the y value ended up being -1/3, and so on, and I started wondering, well, what happens when x is a half or a fourth? What happens to the y value? And interestingly, the y values become integer values again, so they were easier to plot. And by plotting those, that gives us a better picture of the shape of this graph. You may consider including those in your sketch as well. For the next one, the same thing happened. Our data points got much smaller, much quicker here, so instead of 1/3 being the y value, ended up being 1/9. Instead of 1/2, this one ended up being 1/4, and so on. Similarly, by introducing some x values that were closer to the y-axis, we were getting a better view or a better picture of this particular graph. Several of these results did not exist. Of course, we can't take the square root of a negative number in the real number system. By the way, it's worth noting here that anytime I use the phrase DNE, another way to mention that or identify that is that the result is undefined. I tend to use these two phrases interchangeably, even though I think the specific definition, they're not necessarily identical. But DNE, I'm saying that this does not exist in the real number system, and same thing with undefined. The result is undefined in the real number system. So there are, of course, solutions to the square root of -3 and the square root of -2 and the square root of -1. We just need complex numbers to identify them. We're not really focusing on complex numbers at this portion of the unit, so it's okay if we mark them as DNE or undefined. For this cube root graph, again, shouldn't have been any surprises. The x values, however, you'll notice are not consistent. The spacing in between them is quite different, but that was done specifically to generate nice results for our graph. Here's an example of an exponential function. Again, should be no surprises. This logarithm function, which is the inverse of the prior exponential, hopefully you recall that we cannot evaluate logarithms at 0. So I put that number twice in here, and hopefully you recognize that the result does not exist. When the x value is 0, we cannot calculate a logarithmic result. When the x value is negative, we cannot calculate a logarithmic result. There will be no data points to the left of 0 or at 0 on the x-axis. For this v-shaped function, no surprises here. The absolute value bars take our x values and turn them positive. And then finally, these last two examples of semicircles, well, the x values that we provided ended up generating some decimals. Normally, I'm not that interested in the decimals. I prefer precise answers. But it's a bit difficult to graph the y location of the square root of 5 or the square root of 8. So by turning them into decimals, we're able to plot them a little bit more easily on the y, or as a y coordinate. Now, the reason why we go through this exercise is because these are what we call parent functions. This is a collection of parent functions. There are about 8 of them here, even though we've got 9 graphs. And each of these parent functions do have a name associated with them. So when we communicate about the transformation of functions, as we've been discussing so far this week, we can talk specifically about transformation of parent functions, and we can discuss how a parent function is transformed to meet a particular set of data. So this first function, if you are unaware, we would call it a linear function. And in the second example, even though it forms a parabola, we call this a quadratic function. This is the quadratic parent function. And again, this is the parent linear function. This is the parent cubic function, y equals x cubed. And I'll go ahead and provide the names to all of these in just a moment, but what I want to really stress here is that the transformations, the a, b, h, and k transformations that we learned about in the last video, the ones that are listed here in our notes from last video, the a, b, h, and k values can be applied to any of these parent functions, and we can therefore transform it as well. For example, if I write the equation y equals 2 times x minus 5 plus 1, well, that's a series of transformations that has been applied to this parent function. We may simplify this and distribute and end up with 2x minus 9 after all like terms have been combined, and that 2 represents a transformation of this linear function. If we look at this original form, this 2 implies that the graph is twice as tall. This negative 5 inside of our grouping symbol implies the graph gets shifted to the right 5 units, and this 1 on the outside being added implies that the graph has been shifted up 1 unit. Now evidently, because these two equations are equal, they are equivalent, evidently the series of transformations applied here will generate the identical shape by following just these two transformations here. If we were to simply make the graph twice as tall as normal and shift it down 9 units, then we should obtain the exact same result. So in this first example, if I shift this original graph to the right 5 units, we would end up with a graph over here. It looks a little bit smaller because I'm running out of room on the xy axes, but it is the same graph, just shifted to the right 5 units. I'm literally looking at these data points and shifting them all directly to the right. Actually, that's a little bit better. I think I had my slope a little bit off. So now we've shifted this to the right 5 units. Following the order of operations, I would then move to this transformation, doubling its height. So now I want to think about every y value that exists and double it. So instead of having a y value of, well, the y value of 0 when doubled here remains at 0, but the y value here when doubled becomes a 2, the y value here becomes a 4, and the y value here becomes a 6, and so on. So we've got all of these data points. If I were to connect them with a line, we'd have our graph that's been transformed by shifting to the right and stretching taller by a factor of 2. And then lastly, we would have to, whoops, try to slide down here. We would have to then shift this graph up 1 unit. And I think I can probably cheat just a little bit with this electronic ink here. If I capture that and slide this graph up precisely 1 unit, we now have our end result. And this gray line represents our transformed function. And here again, we performed the transformation by using these 3 moves. But with our algebra and simplifying the expression, we see that this was the same. So essentially, this resulting graph, while identified in 3 transformations here, should be the same as this graph, identified by two transformations. We could have shifted this blue graph down 9 units, and that appears to be correct. It looks like we're going to have a y-intercept here at -9, and we have a slope of 2, rise 2, run 1. So I think that's a pretty good representation of the transformations here in 2 different ways. Now for simple functions like linear, perhaps even quadratic and cubic, it may be just as easy to build a table of data, plot those data points, and generate the graph. But in all actuality, when we get into complicated examples, and the quadratic and cubic can be thought of such, it's often easier to consider the parent function and decide how that's going to be transformed in order to locate the new graph and interpret its results, rather than arbitrarily choosing x and y values to plot to that graph. So we'll perform more of these transformations at another time, and you'll see many of them in Math Excel. I'd like to just finish this video by giving you the rest of the names of these parent functions. In a traditional class, when we meet face-to-face, I do give a quiz over the names of these functions, but I don't think that'll be the case this year while we're working in a hybrid schedule. This graph is called an inverse graph, and you'll notice that there is no exponent associated with this x value. And this one is what we would call our inverse squared graph. These 2 shapes are associated with what we call hyperbolic behavior, hyperbolas, and we can regenerate virtually any hyperbola with these 2 parent functions. This graph I'm going to call an even root graph. In this particular case, our root, or our index of our root, is 2, but any even number will behave essentially the same way. The next graph beneath it we'll call an odd root graph. Again, for the same reasons, even though this is a cube root specifically, any odd number used as our index, a 5, a 7, and so on, will generate essentially the same shape. And often it's easier to change the steepness, if you will, of these curved lines by changing the index rather than by scaling it with a stretch. This example, of course, we will call an exponential graph. And anything of this form, y equals some base value to the power of x, would be just fine. We'll consider those exponential graphs. And then this one is a logarithmic graph. And here again, any base value is fine. So we'll write log base a of x. Just do keep in mind that in both of these cases that a is not allowed to be 1, a should not be equal to 1, and a must also be greater than 0. And again, that's true for both exponential and logarithmic equations, and therefore graphs as well. Finally, this one's called the absolute value graph. No surprises there. And then these two examples at the end are both examples of semicircles. Now, there are equations to draw full circles in what we call a conic section, but full circles are not functions. So we're going to deal solely with semicircles. And the generic form of a semicircle is actually going to be this, the square root of r squared minus x squared, where r stands for the radius. You'll notice here that 9 could have been written as 3 squared, and the radius of this semicircle is indeed 3. Similarly, this 81 could have been written as 9 squared, and the radius of this semicircle is, of course, 9. So whatever radius of the semicircle we'd like to produce, we'll square that and then subtract x squared to obtain the expression or the function. Additionally, we could also create the bottom half of a semicircle by including a negative symbol in front of the square root, but that's essentially a vertical flip anyway, so we're not going to include that as part of our definition here for semicircles. We'll simply rely on y equals square root of r squared minus x squared. So to finish up this talking point here, I think it's a good idea to not only memorize the names of these functions, but also to recognize some of their key data points. For example, on this quadratic function, by knowing that the key data points, let's say 0, 0 here is the center or the vertex of this parabola. And if we were to step to the right 1 unit, we would normally go up 1 unit in order to reconnect with the graph or draw our next data point. If we were to step right 2 units from our origin, and we would have to go up 4 units to reconnect with the graph or plot its data point. By recognizing these key data points of the parent graph, we can then make easier adjustments when we transform them. So when this function has to be drawn twice as tall, well, we would just double each of these values. And this one would turn into 2, this one would turn into 8, this one would turn into 18, and so on. So again, it's helpful to memorize these, and it would make your life a little bit easier when performing transformations, especially for the assignments that show up in Math Excel. If you have further questions on these examples, please let me know. Send me a message or stop me in class and we can chat about it. Thanks for watching.